Epoxides are important electrophiles in organic chemistry. The neat thing about them is they are good electrophiles that react almost exclusively by SN2. They are a spring-loaded epoxide. You can think of them as a spring-loaded leaving group, where the three-membered ring is highly strained. So this epoxide just wants to open, and it attracts a nucleophile to open it up. Now the epoxide is actually attached to two alpha carbons. And the two alpha carbons, depending on the epoxides, can be different. It could be epoxide that I have drawn here has two sides to it. The left side is the more substituted side. The right side is the less hindered side. And depending on the conditions, you can get the nucleophile to either attack the more substituted side or the less hindered side. If you wanted to attack the more substituted side, this is typically done under acidic conditions, with weak nucleophiles. If you want to attack the less hindered side, this is done under basic conditions, with strong nucleophiles. Over here, we have two different conditions reacting with the same epoxide. Here, sodium methoxide is a base. It's also a strong nucleophile, and so attack occurs on the less hindered side. The bottom one is under acidic conditions, which is sulfuric acid. We have a weak nucleophile, methanol, so attack occurs on the more substituted side. So, mechanism is actually fairly straightforward. When you're under basic conditions, you have a strong nucleophile that's capable of opening the ring on its own. So methoxide adds, electrons go up, O minus, OMe, like so. And if you notice, we attacked here on this alpha carbon on the right, and so that's the one that gets inverted. Then a quick proton transfer. From the solvent. And you get your final product. Now the epoxide that we started out with is chiral. It's also optically active. That means the product that we end up with, since it doesn't become achiral during any of the process, retains its optical activity. Now, in the bottom case, we're under acidic conditions. Methanol is too weak of a nucleophile to open this epoxide up on its own. So as a result, you have to activate the epoxide by protonating it with sulfuric acid. Now, we have a very, very good leaving group that's ready to spring open. In fact, it's leaving even before the nucleophile adds, and it chooses to lead from the more substituted side, because that's the side that's best able to withstand the delta positive charge that's going to be developing on that. And your nucleophile adds to that carbon. That pops the electrons up onto that oxygen. Since we attacked the more substituted side, that's the side that gets inverted. To finish up the mechanism, we merely deprotonate an oxygen. And we give this as our product. Again, start with an optically active epoxide, and nowhere during the mechanism do we lose optical activity, so the final product is also optically active.